Alright guys, welcome to AtCoder. Today we have ABC 201 and I'm actually early this time. I don't know what happened, but this is what it is. So yeah, I have set up everything I could apart from one thing. So this long story short, I'm using MSVC, as you may have noticed, for reasons that I'm too lazy to install GCC. I don't know why, but I am. So, and therefore I had to manually create a file bitsstdc++.h, and it takes a long time to compile it. So I wanted to pre-compile it, but I couldn't. The tutorial from MSVC docs doesn't work, so if you know a way, please let me know, and it will save a lot of compilation time during the contest. But it's not very relevant to our contest, just if you know a bit more than me, then please share. Okay, so problem A, tiny arithmetic sequence, I suppose. You are given a sequence of 3 numbers, A1, A2, A3. Is it possible to rearrange the elements of A into an arithmetic sequence? Okay, so obviously arithmetic sequences either increasing or decreasing or stable, like all elements are equal. No, okay. So what I want, actually I don't want this, I want, I don't know, vector of size 3. Then I want to read it. I want to sort it, and then I want to check the conditions that they told me, which is A3 gets A2, A1. If this is equal to this, then I want to print yes. Otherwise, I want to print no. So the idea is very simple. Arithmetic sequences, if you look here, if in case it's case sensitive. So here, if this is positive, then this should also be positive. So it's A3 greater than A2, then A2 is greater than A1, and therefore the entire sequence is increasing. And the same works in reverse. So I assume that everyone could figure it out already. So we will just in case anything strange happens, we will test it. Yeah, that's what I'm talking about. It takes more time to compile than I would like it to take. Yeah, okay. Everything's fine here. Problem B, do you know the second highest mountain? So the Republic of AtCoder has n mountains. The ice mountain has a name SI and height TI. Return the name of the second highest mountain there. It's guaranteed that all the mountains have different names and different heights. Okay, so nothing complicated here. I mean, there are multiple ways to do it. You can sort, you can make a linear time algorithm for this. We are going to do, let's say, linear time algorithm just because we can. So we'll keep track of maximum and second maximum. And we can actually do it the fancy way, but we won't. Okay. Second max height. Let's initialize both of them to -1. just in case. Strings are initialized as empty by default, so everything's fine here. Now we take the name and height. Name, height. Now we should update accordingly, so if height is greater than max height, then max name. So first, oh, okay, we don't need this. What we will do instead is, like, first we will update second maximum, I believe. Right. Do it like this. And we update maximum. And we update it by height. And then the same goes for name. So we did this part. Now here, if it is greater than second maximum, then we only have to update second maximum, and we update it to the current value. And what we want to output at the end is, I believe, only the name, so second max name. Of course you can just sort, but that's boring. Also, like, if you wanted to sort, you would have to define a comparator, or at least create pairs in the correct order initially. I don't really want to think about it. So K2, Kita, QC theorem. Okay, I don't know what is QC theorem. Oh, probably the problem setters and their ratings. Okay, funny. Yeah, I also assume that you know how it works. Like, you just have to code it right. And what we successfully did. Problem C, secret number. Takahashi has forgotten his pin code. The pin code is a 4-digit string consisting of 0, 1 through 9 and may begin with a 0. For each digit 0 through 9, Takahashi remembers the following facts. Represented by a 2-character string S0 through S9. S0 I is all if he is certain that pin contains the digit I. He is certain that pin, okay, contain, certain contained, certain did not contain, and not sure. How many strings? Well. Okay. So all that we get is string S, and now we have to think. I will actually make it a bit bigger. So obviously we don't care about specific digits, like we only care how many O's and X's there are. How do you count them? I believe that you can do just like this. And here. And then like this. Yeah, we'll break it into 2 separate lines, because why not? Okay, so I think we counted everything right. Let me just do a little bit of debug real quick. I mean, I'll have to copy the test case either way, so I can just do this now. I really need to invest some time to get comfortable with AtCoder tools. If you have time to guide me through and like through the usage process of some of the tools that you use, feel free to DM me on Discord. It looks like we counted everything fine, so number of x is 4, 3, 2, 6, and 8, 1. Okay. Now we have to actually do something with these counts. Now, okay, man, there are like fast math solutions, and there are also very stupid solutions. I don't even know which one should we do. Okay, let's do the stupid one. Like, because the passwords are really short, you can just loop over all 4 digits. I don't know. Like, I don't really want to figure out this combinatoric stuff, sorry. I can just... Oh, actually, what am I doing? What am I doing? Why did I want to... Like, for what reason on earth did I want to loop over all digits one by one, when I can do just this? So I loop over all possible passwords, and then I think like, okay. Count, we will just count everything that we find good. Okay, now all we have to do is define a function good that will take, actually doesn't have to take s, because we already captured it. Okay. We just generating all digits of a password here, and should have actually converted to like set or an ordered set, because what I'm going to do is for loop over all entries of s. I'm gonna say like if digits, no, if s a digit equals x, then I'm sure it did not contain. Okay, so if digits count digits, right? And I can immediately return false, because the reference string says that the password did not contain something, but our password contains. Else, if the digit is 0, then we want it to contain. So if it doesn't, then we just return false. Again, like reference string says that we have that digit, but we don't. So that's a wrong password. Else we don't care. 108, 0 and 15 are the correct numbers. Of course, this is a terrible solution, but I don't want to think about combinatorics. Most probably you will just end up with some formula with binomial coefficients and stuff. Yeah, but we can get accepted this way and don't think. Usually I feel like in simple problems it's generally good to not think much, because you may just overcomplicate the problem for yourself. Like if you see a solution that fits into the time limit, why don't you implement it like straight away? Problem D, game in Momotetsu world. So we have a grid with 8 rows and W columns of squares where each square is blue or red. Okay. The square at the ith row in j's column is blue if we... Okay, so the input is like this. Okay. Let's start by reading the input. Yeah, reading the input before there is a problem. Good stuff here. Oh, it's vector like strings. Okay. So there is a piece on this grid which is initially placed on the top left square. Takahashi and Aoki will play a game using this piece. Each of the two players has 0 points in the beginning. They will alternately do the following operation, with Takahashi going first. Move the piece 1 square right or 1 square down. It's not allowed to move the piece outside of the grid. The player who moved the piece gets 1 point if the piece is now on a blue square and loses 1 point if the piece is now on a red square. The game ends when one of the players is unable to do the operation, which basically means that we ended up in the lower right corner. If they have different number of points, yeah, okay, this is standard minimax. I don't see a reason why it should not be. Okay, so what is the fastest way to implement it? Let's think. I guess we can just... Oh, I really want to code this in Python. To just use memoization and don't think about anything, but okay. No, let's just call it like, what should we call it? Max score, I guess. That's actually a maximum score difference between the players, but it doesn't really matter. What we should initialize it with? Oh, I don't know, that's not good. Okay, if it's 0, okay. I will just, like, we can initialize with everything if we make sure that the computation order is correct. No, okay. If maximum score, our answer was somewhere here. Maximum score is greater than 0, it means, yeah, maximum difference score, like, it's actually Takahashi or Aoki. Okay, whatever. Like, we will figure out the specific details later. The idea of minimax is just to clear here, like all these games, if, yeah, I just call it maximum. Okay, whatever, it makes sense. So oh, and I also want to think whose move it is. Like we want actually. No, okay, we will check it, it's not hard. And here we should print eDraw. Now we just have to fill the code in. Oh, that was actually... This was input file 1. Yeah, I know it's going to be overwritten. Okay, for this one we'll actually do it like this. So let's see. First of all, we want to know, given a row and column, or I should say I and j, whose turn it is. I suppose that we can do it like this. So if this holds, then it means that hierarchy moves. And how are we gonna H. Okay. We're going to compute in reverse. That's not the best way. Like the best way actually is to use memorization, but I don't feel very comfortable like implementing it straight away in C++ as opposed to Python, so we will try to keep things like this. So first we will, oh, I probably should start from here. Yeah, okay. So here hierarchy moves. Here Takahashi moves. I assume hierarchy, if the score difference is like what is the best score, what is the difference between Takahashi scores and hierarchies? And hierarchy wants to minimize it and Takahashi wants to maximize it, so maximin of I and j will get minimum of maximin of I plus 1 and j maximin of I j plus 1 and we should also take okay, like score of I j plus 1, I suppose. Now score is like a helper function. It will just convert our positive and negative signs into integers. So if aj equals positive sign, then it should return 1, otherwise negative 1. I believe I don't need this, but whatever. Something's wrong. I can feel it, but I don't know what. We moved into that cell, and that's it. It doesn't feel right somehow. Somehow it doesn't. Like, what if actually this I plus 1 is invalid place to move to? Then this score should be really bad. Like, I don't know how much, but probably we can say like numeric No, numeric limits and minimum is too little, like it may overflow somehow, I suppose. How about minus HV? Well, it's like safety measures. Meaning that we don't want to get out of the boundaries of the array. Oh no, it doesn't work like this because... Okay. Yeah, I know what I should do. I will just implement it. So we should not do like this stuff, we should say like only try moves that lead to reasonable squares. And here we initialize with some arbitrary scores to make sure that like they actually try to move somewhere because they are not satisfied with their current position. Oh, I actually should have just copy pasted this. No, the only thing I want here to take maximum and here to take 5%. I still don't like it. There is a problem. For the last cell, it will automatically assign that strange score, right? And it's not good. It's not good. I'm gonna say it like this. So if there is at least one move, then initializer value should be bad. If there are no moves, then you're lucky your initializer value is 0 because the game ends here. You don't have to do anything. We free you from that burden of taking a lot of negative points. Oh, I actually did it wrong. Okay. Takahashi, Ayaki, any draw. Well, that is exactly what's written in the samples, so why don't we just... I still don't like it, how it is. But... maybe it's fine. While I'm seeing things. Yeah, it's fine, it took... No, it didn't take much time either. Okay. You just have to be careful. It's probably much simpler in Python with this memorization, but unfortunately. Okay, let's see what we have remaining. Problem E. Actually, how fast are we moving? Okay. Problem E. Xor distances. We have a weighted tree with n vertices. The i's edge connects vertex y. Ui and vi bidirectionally and has a weight wi. For a pair of vertices xy, let us define the distance of xy as follows: the XOR of the weight of the edges in the shortest path from x to y. Find distance ij for every pair ij such that... Okay, print the sum of those values modulo... Whoa. So we have a weighted tree, sounds like 3DP, is it? The shortest path is obviously unique. Yeah. Yes or no? Let me think. Yes, like. We'll think about... No, wait. Sum of XORs. What? Bro. We have to think how our arbitrary edge partitions the tree, right? So we consider an edge. Suppose that we want to like compute answer by running DFS with some DP. So from every vertex we will return some sort of answer, and it should be useful in a way that should be able to compute the input of that edge into our sum, given that we only, like there may be, UI may have other children, but the thing is like we have the remaining tree, which may look like this actually. UI is here, VI is here, and the answer in VI should tell us how many times the edge between them is counted in the sum, but the distance between vertices is XOR of weights, which I don't really understand. Yeah, the weights can be huge. I am thinking that we can solve the problem for each bit separately. How do we do it? Yeah, imagine that our weights of edges are either zeros or ones. We can do it because the answer only has, like, weights only have 60 bits, so we can do it bit by bit. Let me read the input while I'm thinking about the actual problem and compress that beautiful drawing. Okay, bro. That's terrible way to write it. Let's not do this. Actually, VI is long. What am I doing? Place back. And oh, that's also long. VI, I suppose. Vertices. Okay. Okay, now we have our graph, and all edges have weights either 0 or 1. Now we can do it by bit. Let's actually do this. It's mod. I assume that the mod part doesn't really matter, it's only to prevent overflows. Yeah. Help. I don't know. Solve bit. But okay, now we have to define solve. We actually can do it like all at once. I don't really like to do a lot of things at once. We'll have to compress it even further. Alright, so now we have a graph. It's a tree which we will do DFS on, and we want to so we replaced everything. Oh, I should also do it like this, I guess, because each such edge has a weight 2 to the power of bit. Looks reasonable. Does it? What I don't like is that it can be huge, right? Levels. Oh. I believe I will mod just inside the solve function then. Okay. So all edges in our graph are either of weight 1 or of weight 0. And we should somehow use it to our advantage. I don't really know how to draw trees, so I will just arbitrarily add several edges. Well, let's say blues are 0, reds are 1. For each pair of vertices, we want to take Xor on the path, so that's it. We want to count how many paths are there of with even number of ones and odd number of ones. So I want even and then odd. And then we have some subtree. Let's say like our root is this vertex. This subtree should answer what? It has 2 paths, 1 even, 1 odd, so it will answer 1, 1. Then this will think, okay, I got 1, 1 from here, my edge to that child is red, so I will flip this value, so although nothing changes in this particular case, but it may change here. No, it doesn't change here either. Okay, that's a bit boring. Let us adapt the example. So here we got like how many paths starting like in this subtree with even number of reds is 2, like 2 with 0 red edges, so therefore it will, but this is red, so it will swap them around. And this, from this subtree we get 1, 1, so we add 1, 1 here. Overall we get 2, 3. Then we like this is the answer of this entire subtree. It reports to its parent, which also red edge, so it will be 3, 2. Then we will count everyone who is odd. By this we count in this pass, I believe, and also this pass. And we'll count them into the sum. Okay, sounds like a plan. Can I define nested lambdas? I don't know actually. I assume not, but I don't know why. DFS is recursive, so I will have to write it like this. It takes only one vertex. Actually, I will return pair, because the pair can swap around, and it will be no good if I discard before they, and then they swap. Right, I discarded the value, but then they have to swap, so I failed. And vertex and spot. What should I do? I should return pair of integer and integer. Looks like it has to take bit as well. Really? That's so not nice. Okay. So even odd. We can do it like this, I believe. DFS of 0 and then bit. What we want to return is odd shifted bit to the right. Is it too much or is it not? I feel like it may be too much. Okay, we are not going to risk it. Here goes a stupid for loop. Actually, yeah, just because you can have a lot of paths, basically 10 to the 5th pass, 2 times 10 to the 5th, and you cannot just shift them 60 times because it will clearly overflow even in longs. So what do we do here? We say like int. Or actually, should we have visited array? Because I don't know who is parent and who is not. Bro, that's getting out of hand. That's too much. I must be implementing it like terribly wrong, but I don't know what to do. What else should I do, like to make it better? I think I can assign in zeros. I believe it's like size first and then number because it makes sense because all containers work like this, I assume. What am I going to do next? What am I going to do next? I should count odd and even that start like here in this subtree. I also should say like visited at vertex gets true. I want to loop over all neighbors of this vertex, I assume. If they are not visited, I want to compute the answer for them. DFS of neighbor, and the same bit. Now if, oh, but it's not like this, it's neighbor and then wait. If wait has this bit turned on, then I want to flip. Otherwise, I don't want to flip. No, it doesn't look that bad actually, once I think about it. I believe I did a terrible implementation, but who cares if we get accepted, right? That's all competitive programming is about. Oh, nice of them to provide big tests. I mean, tests with big numbers. It doesn't exactly mean the same. not good, not good, not good. This is not good. Oh, I assume that if it has nothing, then there's one even pass, right? Because yeah, we like do this, but then we don't have a best case when this is empty. Not exactly like this. If there are no children who are not visited, so if it had some children, then we want to return these children. Else we want to return, I believe, 0, 1, because there is one pass of 0 edges. Sounds reasonable, but I may be very wrong. Not good, not good. What is that test actually? E1 it was. Funny. Well, not exactly they are rather false, but it doesn't matter. That doesn't matter. I think I should just debug it. Oh, I know what went wrong. Let's double check. First goes odd, then even. Odd, even, odd, even. Sometime I hope it solves our problem, because otherwise I don't know what is wrong and we will need to debug. No, it doesn't. Okay. Tough luck. Wait. It looks like we should just start even with 1, like in all cases, because we care about incomplete pass as well, right? I think it's so. We can end this debug part. Just in case we need it, I'll finish this. Looks reasonable, okay. So like, we don't only think about paths from root to leaves, but we also think about all the paths in between. And still it doesn't work like this. Maybe, oh, because I'm still counting paths from root only, right? Whereas what I really should do is don't do this, but rather say like, hey, well, we'll have to return it, right? But I should count all the paths that end no matter where. Am I right? Oh, we'll only need some odd actually. Yeah, let's just call it some. I hope it can no, okay, it says like undefined because it should be defined here, I assume. And it also should be long because it can very easily overflow. And everything here should be long and it's getting terrible. Okay, whatever. Now we define sum, and here we don't want to do that, we want to do that, I think. Yeah, because we want to count paths that start everywhere and end everywhere. Oh, anywhere? I don't really know. No, it's still wrong. I assume that there is no other choice and we'll have to debug it like this. Wait, what? Oh, okay, because we have a lot of wrong bits. I'm surprised for what reason we have one odd insert sort bit. Wait, no, like, hold on, E1, sort bit. There is nothing. Sort bit should return 0 for every odd value. And we get in bits like 1 and 0, and this is reasonable because I'm actually surprised why we are not getting ones in bit 2. Oh my God. What did I do wrong in my life? Or maybe that's not long. Is it the reason? Like, really? No, I had to recompile it. Oh, I assume that's why you want to 4. 4 is not correct because we did not have bit 2. Oh no, bit 1 is actually correct. Bit 1 is here and it has one pass, one odd pass, but it should be 2, right? It should be 2. No? What am I missing? Like, bit 1 means that we're looking for 2s, which, like, let me show. The first graph is like bit equals 0. This is the graph. And bit equals 1, this is the graph. So this should be counted in pass 1, 3, and then 2, 3. Right? Oh. What? But how do I? Okay, at the moment my problem is that I'm only counting paths that go down in the tree. They can start everywhere, they can end everywhere, but I don't I don't count paths that go like arbitrarily in the tree, which is terrible. Oof. How could I make that many mistakes in the same problem? Okay, I must be very stupid. How to count these paths that go from left to right? I will count them at the point where they join, or at least I should, but oh. I assume that I should count them like this. Like whenever I am in this vertex, okay? In this vertex I have already seen some paths in that subtree, and now I'm starting to see paths in this subtree, and I should multiply all of these paths with all of the paths that should be here. That are already here. Paths that are already here are in odd and even, and new paths are in n odd and n even. And I should do it before I do, so we count in odd paths. Because here we flip, we swap, and here we don't. That's a lot of logic to keep in mind at the same time. Okay, not bad. Sorry, I have to clear it because... Oh, it's not... Oh, I missed the key. Okay, 62 is the correct answer. For 3, it is... looks correct, apart from us printing too much. So let's just comment and make sure that everything still works. Okay, I think I count all the paths correctly now. It took us, yeah, I'm just stupid. I did not think about how do we count paths. I hope it doesn't CLE, actually. Because maybe we should count all the bits at once, but I hope we don't have to do that, please. It's taking a lot of time. Must be like 1.9 seconds. 2.2 out of how much? Oh, the time limit is actually increased for that problem. Interesting. So we did, I assume we did the expected solution, because otherwise, if it was not expected, then what is the reason they raised the time limit? Okay, okay. We still have a lot of time to solve F. Problem F, Insertion Sort. There are n people who are given ID numbers 1 through n, standing in a row from left to right. Initially, the ID number of the ith person from the left is pi, so I have a permutation. While our objective is to rearrange the people in ascending order of their ID number from left to right, ascending, okay. By repeatedly doing the 3 kinds of operations below, you can do this operation any number of times, possible 0 in any order. So first we can choose an integer I, pay the cost AI, and move person I to any position of our choice. Cool. We can choose an integer I, pay the cost BI, and move person I to the left end of the row. We can pay cost CI and move person I to the right end of the row. And obviously I want to minimize the total cost. That requires some thinking. It requires a lot of thinking. I don't know straight away how to solve it. Bro. Oh. I'm still a bit disappointed by how much time we spent on E. How do we permit people with minimum cost? Possible ideas include that first you can move somebody to the end you should be at. Then does it really work? I don't think it works like this. Let's create a structure. No, I don't really want to. Okay, we'll just call them A, B, and C. Oh, I don't have to do that. What am I doing? Person B, person C. Hope you can derive constructor yourself. Oh. Probably should not do this, but whatever. No, I'm going to take a break here because it's just, I was thinking too hard on the previous problem. Sorry guys. It's supposed, I don't know, maybe it's a bad thing to do from the screencast point of view, but I don't know, it looks like I have to actually seem to solve this problem and I don't feel like it right now. So yeah, I guess we'll just end it here. Like, we still have a lot of time despite the break that I took. We still have, I don't know how many, 27 minutes, something like, oh, that's not the right contest. 27 minutes, but I don't really feel like thinking. Yeah, 25 minutes, whatever. Bro, I feel like I'm letting you down a bit in this one, but like, probably the general idea is actually that we want to move people to the left or to the right. I believe we don't want to move people arbitrarily, and the only use of value AI is that BI should become minimum of BI and AI, and CI should become minimum of CI and AI. After that, you more or less want to shift some people to the beginning and then shift some people to the end. Actually, the order doesn't really matter. because you can always fix the order afterwards. One observation that I had is that it never makes sense to move one person twice, because you can just use whatever was the latest move in the latest moment. That doesn't make any sense. Then, like, there are still implementation problems, maybe even logic problems with this. Like, I can find what is the cost to move first I people to the left and then all the remaining people to the right, right? And you may say like, okay, both of these are like computable with one scan and second scan. So one is like, for every prefix we compute what is the cost of shifting this prefix to the left. For every suffix we compute the same thing. And you may think that we can just take minimum of such costs, like before I to the left, after I to the right. But it doesn't actually work, because sometimes you're lucky from the cost point of view and unlucky from the coding point of view, because after we shifted like first 2 people to the left and last 5 people to the right, it may magically happen that the remaining 3 people, or however many people we have, the remaining people may just already be in the correct positions, and we don't have to shift anything. And I don't really know how to address this issue. I assume that when we are building like the prefix cost array, we should put everything into a priority queue with the following idea in mind. Like, we would like to know quickly whether after first I operations, I plus first person gets to the correct place. If it does, good. If it doesn't, then we have to pay for it. Then I sense problems, like, because with such approach. Because if we had like some lucky people, then unlucky people, shifting them somewhere may actually require shifting that lucky people in front of them. That's just, I don't really know how to address this from the logic point of view. Probably you can do something like this, just be smart about it and it will work, but I don't really feel like figuring out all the details now. Plus, I mean, I have a contest later today, and I already started feeling like I was thinking too much. Maybe that's not good for the upcoming contest, so I guess I will have to end it here. I don't think that I will come back to it immediately after the contest. Maybe tomorrow, but don't really feel like this. I don't know. Tough day today. See you in the next one, I believe. Because I really don't want to solve it, I don't know. I believe you can understand. You also have such problems that you don't really want to solve. It doesn't feel like particularly beautiful either, so that's what I can say. Bye guys.